Yep, are we good? Okay.
Yes.
Good. Welcome to the second part of this evening. My name is Jeroen van Disseldorp. I'm CEO and founder of Actual, and we provide streaming platforms to our customers. I'm not going to talk much about that tonight because this is mostly going to be a technical talk, but to give you a little bit of background on what we do. We sell Kafka mostly to bigger organizations as a central hub for sharing information internally and with business partners if necessary. So this is mostly our model, having a central hub where all of the quote-unquote now information is shared, which is being presented to teams that want to use Kafka as a multi-tenant solution. So it's it's a little bit more than Kafka. It has a self-service UI on top, which we developed ourselves, in which you can define teams and you can assign roles and rights to teams, what they can do on Kafka themselves. It's on-premise in the cloud, secure and compliant, blah, blah. But what we are going to focus on tonight is mostly the developer productivity, because that is what KSML intends to achieve, higher development productivity. And this whole idea started out when we were a bit bored a few years ago, sitting at home, having not much to do, no meetups. I started playing around with a tool called Home Assistant, which allows you to automate your home, basically, get all kinds of sensors information in and try to have your home do smart things, the things that you want done. Now, I don't know if you know Home Assistant a little bit, but Home Assistant uses a thing called scripts. And these scripts allow you to define your own simple automations. A script like this, where you say, well, this is a bit defined in YAML. This is what I basically want to have done. In this case, I want to send a notification with a certain message. These scripts can get quite complex, as you see on the left. They can be quite long. But while I was playing around with Home Assistant, I started to draw some parallels between what we intend to do with Actual and also what Home Assistant allows you to do with YAML. The nice thing is that it's no coding, it's more like configuration. The YAML is treated more as a configuration thing than as a coding thing. It's a domain-specific language. It has automations, it has script, it has sensors. It requires no compilation. It just requires you to script something in a particular format, and then it interprets it and runs it for you. So that got us thinking. In the Kafka world, we see a lot of teams struggling with defining Java projects, setting up build pipelines, having all kinds of boilerplate stuff that they need to do in order to get a Kafka Streams application going. So what if we apply this whole Home Assistant YAML thing to Kafka? What could we get done? So with YAML, we could specify a Kafka Streams topology. So the theory that we had was, well, what if we have a certain YAML specification, we throw it in some interpreter, and out comes a streaming application running for you. How nice would that be? And an example would be, well, suppose that you define this particular pipeline. With Kafka Streams, you define your pipelines. Something comes in and you take a series of steps and something comes out. So what if you were to define such a thing like this? You have a pipeline called main. You read from some topic and you output to some other topic. That would already give you a copying pipeline, copying messages from one topic to another without too much work for that. But if you know Kafka Streams a little bit, it's quite an extensive framework. Kafka Streams has a lot of functions that you can inject. Predicates for filtering things. You can do transformations of key and values on Kafka. You can join values, merge streams and tables. So could we somehow specify these without requiring the compilation in YAML? So we started an investigation. Well, after a few deviations, we ended up with GraalVM, which is a very nice Java virtual machines that not only allows you to run Java code, but also allows you to run Python code. And Python, of course, is an interpreted language. So the idea we had is, well, what if we could generate Python code as Java strings and feed them into the interpreter? And then load your custom functions in GraalVM and have them executed for you. How nice would that be? So that is what KSML turned out to be. I'm going to show you lots of that in a minute. But before I do, one of the cases that we worked on last year, actually for NHN, was a use case that they presented to us as part of their RFP process, where they said, well, we have municipal home care service providers, and these basically have sensors hooked up to patients. And we want those sensor readings to come into a central point, to a central Kafka. And we have, well, different kinds of measurements that we do. And we want to be able to process that information and hand it off to statisticians that can derive certain statistics from the data they get fed. A couple of things. Sensors are hooked up to patients, something that we called an assignment. So if I have a heart rate sensor and I hook it up to you, and then, well, you die, or you don't need it anymore for some reason, I hook it up to some other person, it has to have a different assignment ID, because I would never want to mess up your heart rate with somebody else's heart rate. So that's what we call an assignment in this particular use case. Measurements are done anonymous, so there's always the key of a message for a measurement is an assignment ID, and that is shared in the measurement itself. Patient records are only kept centrally, so patient records and the personal identifiable information is only kept centrally. The end goal was to get that data, the measurement, de-anonymized, so you have to merge it with assignment ID, then you get a patient ID, and then merge it with patient records, and out comes a measurement with patient records. That is something that we set out to achieve, but it was still in an RFP process, so we didn't want to spend too much time on it. So all that I'm about to show you was set up in the course of, I believe, 1.5 or max 2 days. To give you a bit of a feel of how much time it took. So we're going to demo this and have some live coding if time permits, but primarily I'll be focusing on the use case itself. Now for this, I'll sit down because it makes it much easier to share my screen. So let me focus on the use case first. So this is the topology that we set up. So initially you have these 3 health data providers. The 3 health data providers are outputting measurements to their own topic. These are the measurements with the assignment ID as key and the measurement itself as the value. And what they also sometimes give you is new sensor assignments. So they'll be producing new assignments to this particular topic, which is then later used in a stream merge. Well, in the demo, just for the fun of it, we have 3 kinds of measurements coming in from provider 1. It's sleep, it's heart rate, and oxygen saturation. We made a health data router simply to show off how you can easily sort these kinds of messages, giving 3 new output topics, 1 for heartbeat, 1 for O2 saturation, and 1 for sleep. After which we'll do the stream join. And the stream join is then taking in the sensor assignments together with the other topics, and we'll be outputting sensor measurements with patient assignments, and this gives you a patient ID, which we then finally merge with patient records, and out comes a measurement together with the patient information. Now, I don't know if you've... Well, sounds fun out there. We're in the wrong place. So I don't know if you've ever worked with Kafka Streams before, but it's quite the beast if you want to undertake this kind of processing with Kafka Streams. Not because the business code is so much, that's not too much. I think every task expressed here as a separate application is something that you can just catch in one screen of Java code. But it's the whole hassle of having to compile it, having it thrown it through a pipeline, having to compile that into a Docker container. It has to run somewhere, and then you have to monitor and maintain it, and all that. It is a lot of hassle. So we decided to use KSML for this, and simply to give you a bit of a feel how realistic we try to make it, we actually looked up messages, this is a site called OpenMHealth, which contains a lot of schema for the health sector on how you can share messages. So we looked up a heart rate message, we have a sleep duration message in JSON here, and we have a oxygen saturation message here. And we're going to generate some random values. The first thing before we can start processing is to generate the data. So I'm going to show you how that works in KSML. We have a bunch of files here on the left. I hope the font is readable in this format. A bunch of files here on the left which contain all the sensor information and the patient information. So provider 1, we just have something like a social security number. This is all fake information, by the way. We generated this, but it had to sound Norwegian, so we actually looked this up and what are the most common Norwegian names. So it's like a social security number, first name, last name, an address. All is fake, so no worries about showing it here. Birth date, and we had 6 food preferences, like this person loves chips or loves vegetables, and like a +1 was you love the food, and like a 0 was neutral, and -1 you don't like that particular food. So that is used. We have heartbeat sensors, just a bunch of random generated data. This is a heartbeat sensor ID and a brand associated to it. We have sleep sensors. That's also just a fake list. And we have oxygen saturation sensors. And this all per provider. So you see this, this list copied here. The sleep sensors, they are exactly the same in the oxygen saturation. They just have different IDs. So the first digit is actually the provider that it comes from. All right, so let's take a quick look on how we can generate the data, because that was like task 1. How do we generate data which actually represents something, or it tries to mimic reality at least? So in order to do that, we wrote a bunch of data generators here in KSML. Let me go down first so you can quickly see. This is the biggest file, by the way. So we have a couple of producers here. If I start this script, it will start just randomly generating information. We have a patient record producer, which produces a message every 500 milliseconds. And it does so by calling this generator function, and it outputs the information to this particular topic. So that gets rid of all the patient information that's being dumped on specific topics. Then we have the generation of these assignments. So this is done every 15 seconds, so not too much. You can see in the beginning, if I start up the scripts in a minute, then in the beginning there's not too much joining going on, because it first has to generate the proper assignments. And that is only done every 15 seconds. Well, I can maybe make that 10 to get it a little quicker. And there's a couple of sensor readings that we fake. So provider 1 generates heartbeat sensor messages every second and outputs it to this particular topic. In a key is the string, the assignment ID, and the value is the measurement itself. And we do that for sleep, for oxygen saturation, and for all the other providers. Again, let me give you a glimpse of what that looks like in the KSML. So in order to generate the patient record, it's relatively simple. We have a function that we call type generator. It uses a global variable in the Python context called providers, where all the provider information is kept. We let it choose a random patient, get the social security number out, and that is the key value that we produce on the topic. Let me quickly start this up and you can see what it exactly does. So there's a bunch of producers here that all produce a part of the demo data. And that is what is going on right here. So in order to look at this a little bit more specifically, let me go back to self-service. You can look here on the left. There's measurements coming in. You can inspect the messages. And the measurements that are coming in are really the realistic type of messages. So in this case, we're looking at a heartbeat measurement from provider 1. It has an effective time frame. There's, the now information is generated. All of this is done just in a few lines of YAML and Python, and it looks really realistic, right? So this is a random value that we generate. So measurements are coming in at the moment. The same thing with the patient record information. So if I look at patient records, you can look on the messages here. You'll find that there's really like emulated data coming in on the patient records. And the same thing is for the assignments that we have. Looking at messages. There's really like an assignment ID, which is a UUID that gets generated. A patient ID is one of the patients from that particular provider, which now has sensor, sleep sensor SL35 associated to it. And from this point onwards, every message that gets produced for sensor assignment 432 blah blah is automatically associated with this patient ID. Now, the generation is one part, but of course the processing is much more fun. So let's look at the first step. While the generator just keeps on producing here in the backend, let's look at the first step. So that data router that will separate all the information out and makes sleep messages go to one topic, heartbeat to another topic, etc. What we do here at the top is we define what source streams that we have. So here we say, well, this is a source stream measurements provider 1. This is the topic. The key type is the string. That's the assignment ID, and the value type is a JSON. That gets parsed into a pipeline. So this is the pipeline for provider 1. We read from that particular topic. We then say, well, transform the value. If we're going to dump all the sleep messages on one topic and all the we're never going to find out, or we're never going to know what the lineage of that particular message is. So we're adding a field to make it traceable from what provider we got this initial message. So just a transform value will allow us to add a field to the JSON that we get in. And we set the value, in the value we set the field provider to provider 1 in this case. We dump it to standard out, just to get some messages out on the terminal to see that stuff is being processed. And we then send it to a router function. And the router function is defined above here. This is the router function, which is a topic name extractor in Kafka Streams. You define that. The type is the sensor type that we get out of the value of the Kafka message. And we then say, well, if it's oxygen saturation, then send it to this topic. If it's heartbeat, send it to that topic. And if it's sleep, send it to the third topic. Now I have to enable this script. Oh, this is enabled already. So if we then start to run this, you're going to see that it receives a lot of messages from that particular provider. You will see that the provider field here is now, oh, if I pause this, there's a provider field here added. So this is the mangling that we do per provider. We set an extra field. And the nice thing is that if we go back to the topology, you can now see that if we look at sleep, for instance, and I search on messages for the last hour, all messages here will be of type sleep. So here, the sleep duration of type sleep. So this is a very easy way to sort all these messages. We don't care necessarily in Python if this is an Avro message, an XML message, a JSON, or anything else, because Python just knows about dictionaries and whether it's sent as an Avro message or something else or XML, that really doesn't matter. It's the internal format of KSML. And if you just send it off to an XML topic or to an Avro topic, it will translate it automatically. And that's irrespective of how it's internally represented. So in KSML itself, you just need to worry about, how you would capture it in a Python dictionary, and not much more. Now, the second step would be to do a join with the assignment. So let me already enable that in the scripting here. And that's also relatively easy. We declare all the streams and the tables that we use above. So we read from 3 topics. And we output to this particular topic. And we use a join table here as the sensor assignments table. We have an enrichment function. I'll come back to that in a minute, but let's inspect the pipeline first. So the heartbeat enrichment. We have 3 topics coming in, so we have to specify this for every measurement type. We read from heartbeats. We enrich that with a particular function, and that's the function defined above. So what it does is it will get one measurement, and it will get one of these assignments with the same key. So it will be able to extract the patient ID from that particular assignment. And what it already does is it prepares the Kafka message for later processing. So what we here do is we ignore the current key, but we reset the key to the patient ID gotten from the value. So we can do an automatically we can do a join after this one. And then we send it off to a particular topic. Well, if we start running this next to the measurement router, you can see that there are messages coming in. And if we look at the individual topic again, that's this one. Messages from the last hour. You'll see that there's now a measurement value. Oh, I didn't show the value joiner just yet, but we set a field measurement. So we copy the old value in a new dictionary on the measurement. We have a patient ID now and the sensor ID in the sensor type. And that's exactly what we specified above here. In the joining function, we get value 1 is the measurement, value 2 is the assignment, and we output an enriched measurement simply by saying the joint value. We set the measurement element to value 1, patient ID is copied from value 2, and sensor ID and sensor type are also copied from value 2. And that's how easy it is to do a join. Well, the third, the script is not much different. We read from this particular topic, we join it now with patient record information, and we have an enriched measurement with patient records. So let me enable that script here as well. Start that up. Yep. There is definitely the demo effect. It had to go wrong at some point. This is, I know this, I think. And we can now start to look at the topology. And then specifically, if you look at these messages, you can now see that the measurement is there. The patient ID is still there, but we now joined it with patient record information. So this is now a simple join with an external table that allows the statisticians to process the information and start generating their statistics. Well, all of this is relatively easy to do. KSML itself has a lot of different functions. If you want to play around with it, there's a bunch of examples in an example directory here as well. What you can do, you can count, you can aggregate, you can convert messages, and it really doesn't matter in what format the message is specified. It will just decode, give you a Python dictionary or a list object or something you can manipulate and have it written out to some topic again. All right, any questions on this?
So schema registry, does it work with?
Yes, it works with schema registry. So if it's an Avro message, it will automatically get the Avro schema from the registry and use that as the schema going forward. You can actually see that. I didn't show that in much detail, but the generation of the patient records. This is actually an Avro patient record. So this is not a JSON, but we have a patient record information in here. Oh, not in this directory. This is a schema in Avro that it uses to encode the message. So it will just copy the values from the Python dictionary into this particular schema and they use it as such. And there's even a patient record CSV. This is the one where there's one line of just comma-separated column headers. And it uses this to decode the patient information here. So what actually is done with the generation of the patient record is, if you look at the generation function here, mind you, it's written out as Avro, but the patient information itself, it's just getting the comma-separated line from the patient's file. It gets the social security number as the first element, but it returns this tuple with a CSV patient record. And that makes KSML automatically interpret it, throw it through the interpreter, so it will extract all the fields and apply the column headers, and it will convert it automatically to a Python dictionary. So that's a very easy way to also generate test data if you have some, or so you can have a result type of a particular function and have it interpreted by KSML regardless of in what format or to what topic something is produced. Well, I was going to do some live coding, but I did prepare 2 examples just to show you how easy it would be to write your own functions. And this is really a small example. So suppose we want to read from provider 1. This is the topic definition here. We can then say, well, I want to read from this topic in a particular pipeline, throw it through a heartbeat filter. So only sensor readings of type heartbeat will be passed. And then you can output that to the log in this case. Another example would be that you can read from the same measurements topic. Well, you can say on the log what kind of message you found, but let's suppose that we then want to aggregate that. So we're going to group messages by brand. This is, here you see there's a custom function injected here where we say if the value, if there is no sensor brand attribute, we will set it to no sensor type. But normally there is a sensor brand attribute, so we'll just return that. So we're going to group on sensor brand. We're going to window it by a particular time in tumbling windows of 20 seconds. We want to aggregate that. And at the end, we're going to convert it to a stream and dump it on standard out. Let me enable this one. And disable the other ones. Now if I start to run this, then you'll automatically see that, yeah, this is all good. Is it? No, it's not good. Oh, yeah. There is a topic missing because this is something that I didn't create yet. There's a topic missing for the repartition. So let me quickly create that. Going to create a new topic. It's going to be called this. It's a repartition topic, and here you can see you can assign a certain DevOps team as the owner of this particular topic. Is going to have the string JSON type, retention policy of deletes, and we're going to create that. Once it's created, we also have to set it up in the proper environment, in the health demo environment in this case. So I'm quickly going to do that. And then to the this application that will process the information. So normally this would be owned, well, you see it here already, it's owned by a different team. So this team can add a request. So I want to be a producer to the repartition topic, request approval. But as a streaming application, I also need consume rights. So I also want to consume this topic. And then I can go as the topic owner to that particular topic. There's 2 exclamation marks, meaning that the access rights haven't been granted yet. So I'm going to approve this request, and now this application has full produce and consume rights. And then to restart it, and now you can see that the messages are flowing in. Aggregation is done in windows of 20 seconds, so it will probably take a little bit of time before we see some values coming out. Yes, now here are the aggregation values. So here there's an aggregate coming out of this calculation for this particular window of 20 seconds. The key is, well, you can see that here is the brand of the sensor that we're using. And if you go all the way to the right, you can see the value. This is the number of measurements it actually counted in this particular window. So that's a very easy way to count number of messages in a particular time window, or maybe to do some other kind of aggregation. You can of course mix and match. You can also add the total heartbeats of all patients that were measured. So you can do all kinds of fancy calculations. But it's a very easy way to specify what your streaming application needs to do without going through the hassle of writing all this Java code. So going back to the presentation. So in summary, well, we started out with this KSML thing as an experiment, but it has proven to be quite powerful already. It's really low code to allow you to express streaming applications in a few easy to understand lines of YAML and Python. It's fast. I mean, if we would have done this demo scenario with real Java applications, it would have taken us weeks, maybe months. But now this was something that we just specified, and we got it up and running quite quickly. It's multi-tenant, so it runs on your behalf, meaning that if you have a DevOps team, you can just specify your own YAML, have a container run, interpret the YAML for you, and have it run on your behalf. And it's open source, and it's published on GitHub. So if you want to take a look, or if you want to experiment or become part of the community, by all means, join in and let us know what you experience with it. Thank you very much. Any questions? Yeah.
Can you explain that a bit?
Yeah, that's something that is a part of the Kafka Streams windowing specification. I think it was in the last example, right? In this, I think it was here. Yeah, this one, or the caching. Yeah. So what you can choose is whether all the output that you saw in the aggregates I think it was here. Yeah, you saw it being dumped. It started here. And then it was dumped. The whole time window was dumped at once. So that is caching true, meaning that you get output only once every 20 seconds. So all the intermediate results, they will get just cached until the window really closes, and then you get all your results. If I put this to false, I can rerun it. And then what you'll see is that throughout receiving the messages, it will just dump all the intermediate results right away. While counting, it will give you every intermittent result. Yeah, so this is the rebalancing of Kafka that we sometimes get stuck with. It can take up to 30 seconds before the application really starts. If you just quickly stop it and restart it without setting the proper consumer group ID. So, well, you can sit this one out, but as soon as the output starts running, you'll see that it will start receiving messages, but intermediately it will start outputting these aggregate messages. See, now it's a found message and it dumps the aggregate right away. Found message and dumps the aggregate right away. So every input message will lead to an intermediate output of the result so far, and that's what caching does.
Yeah, very good presentation. It reminds me of Argo workflow.
Yeah.
You can declaratively, specify, what you want done, and Argo does it for you. Yeah.
Right.
Yeah. So I just wanted to ask, internal topics.
Yeah.
How easy it is to specify the internal topics, because Kafka Streams generates the internal topics.
Yeah.
Right.
Yeah.
If you want to pre-configure the topics, right?
Yeah.
How easy it is to do that with
KSML. Yeah. So it's only one letter different with KSQL. So this is really, it's like Kafka Streams Markup Language, right? So unofficially. So the intermediate topics, they have a fixed format. So it's the application ID from Kafka Streams, and then I believe dot, and then the store name that it uses, and then maybe a dash repartition or a dash changelog. So that's the fixed format. In the runner specification, so the YAML file that defines what you will run and where to connect to Kafka, this is also where you specify the application ID. So it will read the application ID from this, and that's why health data router was in this particular topic name, because it will use application ID and then the name given to it by KSML. So the group by brand is something that we specified in the script. The inspect measurements is actually the name I gave this particular script. And the repartition is something that, you can't get around, because that is what Kafka Streams appends for you. Yeah. So it's a fixed name, and it's really easy to create these topics. It will always have the same name. So we happen to have a really secured, closed down Kafka. So you have to create these topics up front, because they have to have an owner, and that owner needs to adopt the topic, and you don't want to have orphan topics floating around in your organization. So that's why I quickly created it. But they have a fixed format, so it's relatively simple to set them up.
Okay.
Yeah.
So you can run a diagnostic kind of like execution to print the internal topics, so that you can then create them.
Yeah, if you want to look at these internal topics, you can exactly see what kind of information is kept. So here, this is the key, and you can see what kind of information is stored in that internal topic.
Yeah, that's fine. Perfect.
Yeah.
Thank you. Yeah.
All right. Any other questions? All right, then I would say thank you very much, and enjoy the drinks while you stay around.
Okay. Thank you.
Everyone else helped us all there, so fuck in.